So as I said, Dr. Dawood Moumini just left the session. He has to chair this session, but he had some issue, and he asked me to chair it. So go ahead, please.
Thank you. So first of all, I would like to thank the organizers, especially Dawood, to give this opportunity to me to present my work here. The title of the talk, as you hear, is the first law of holography complexity. And this work is based on collaborations with Qadir Jafari and Sedeqe Hashemi, both of them from the IPM, School of Particles and Accelerators, and lots of discussions with other people, especially in IPM and Sharif University, Amin, Mohsen, Mehregan, Farzad, Muhammad Risa, and Hamid, and some other people that I forget to write the names on the concept of complexity, computational complexity, and the holographic complexity. I will explain with some details these concepts for you. Let me remind you that in the recent years, the idea of quantum information theory have played an increasingly important role in shedding light on dark corners of quantum field theory and quantum gravity. One of these concepts that comes from the quantum information theory, as you know better than me, is the entanglement ontropy. Especially the entanglement ontropy for conformal field theories is proposed by Ryota Kaneki to be a minimal codimension 2 hypersurface in the geometry of asymptotically locally ADS spacetimes. Interestingly, this proposal is used by Swinger, and he combined it with the idea of mirror tensor network to show that the gravity is an emergent quantity, in that it emerges from the entanglement. Let me explain a little bit more for you this figure. This figure is actually related to the tensor network of the mirror. Mirror is abbreviation for the multi-scale entanglement renormalization ansatz. In these tensor networks, you in the bottom of the figure, actually you have your original system. What I mean about the original system, I mean it is described, for example, a vacuum, a state of a Hamiltonian of a system that is discretized on the lattice. Each point in the bottom of the figure is related to the spin. You can see two different operators in this figure. One of them, which is the square one, and people in the community call it entangler or disentangler, based on the directions that you have passed to the bottom or to the lower layers or to the upper and upper layers. It's, I mean, just the name. If you come from the bottom to the up, it's translate to the disentangler, and in the reverse side, it means entangler. The rule of this operator is creating in the entanglement or increasing the entanglement between the points. I mean, the entanglement in my talk means the bipart of entanglement control. The another operators is, we call it in the literature, the scaling operator. It is similar to the scaling operator of the Wilsonian renormalization group. But what was the idea of Swinger for his very fascinating proposals? If you consider a region with the length L, for example, in the first line in the bottom of the figure, and then found spatial curves with some constraint that is it is related to the some notion of the causality in the tensor network of the mirror, the lengths of these spatial curves that I showed to you with the dashed red ones in this figure, the length of these spatial curves is proportional to the logarithm of L, the size of that region. It is very interestingly, it is nothing just the entanglement ontropy of a subregion with the length L in the conformal field theory. This figure is very similar, and also the curves, similar to the Ryota-Kaneki curves in the background of the time slice of the ADS spacetimes. So this is the point that the Swinger by it claimed that the gravity is an emergent quantity which from quantity, the quantity is the entanglement entropy. That, as I told to you, the entanglement entropy is the main concept in the tensor network of the mirror. Let me add another interesting point to the tensor network of the mirror for you, and it is its relation to the renormalization group. The simplest way to understand the relation of the mirror to the renormalization group of the Wilson is as the following. Let's consider, for example, a massive scalar theory, and then do the Wilsonian renormalization group on it. In the end of the day, you find a theory just with a mass term. I mean, the kinetic term can be neglected in the very deep IR in comparison to the mass term. So just the mass term remains. And when the kinetic terms can be negligible, so therefore the entanglement entropy can be zero in the final state. And it is the structure of the mirror. As I told to you, one operator, which we call it this disentangler, its rules is decreasing the value of the entanglement. So in the end of the day, in the last level of the tensor network of the mirror, the state is a product state, and so it is a state with zero entanglement entropy. So moving it to the inside of the tensor network of the mirror can be translated to the idea of the Wilsonian renormalization group. So you can see that some concept from the quantum information theory, how can be related to the very different notion in quantum gravity, I mean time slice of ADS and ADS CFT, and another different concept in quantum field theory that was the Wilsonian renormalization group. But albeit this is a genuine idea, but it is discussed by Syscon that the entanglement entropy is not enough. The simplest way to see it in the gravity is noting to the geometry in the behind the horizon. I mean the interior of the black hole, where the rule of time and another coordinates, which you can call it, is changed. And so the geometry behind the horizon is time dependent, but the original that metric that we have started with it, that it described the geometry far from the horizon to the asymptotics is stationary or statics. So the entanglement entropy, because some constraint that comes from the definition of the entanglement entropy, I mean the homology constraint, the Ryota-Koinagi surface cannot penetrate into the inside of the black hole, so it cannot describe the geometry behind the horizon, and so it cannot describe the time dependency of the geometry in that region. So you need to another quantity from the quantum information theory to describe also the interior of the black hole. And Syscon proposed that this concept from the quantum information theory is actually complexity. We have different notion of the complexity in the literature. Sometimes you see the state complexity, operator complexity, circuit complexity, and so on. In this talk, my main focus is related to the circuit complexity. In the simple language, the circuit complexity or quantum circuit complexity can be described as following. In the quantum circuit complexity, you need, apart from the target states that you have decided to define or finding its complexity, you need two other extra objects. One object is the reference states. The reference states can be any states, but in the literature, in the community, the people choose it as a product state similar to the states in the mirror tensor network. It is a state that the bipartite entanglement entropy for it is zero. Another object that you need to define the circuit complexity is a unitary transformations. For example, in the tensor network of the mirror, it was entangler and scaling, but in general, you have different cases or different options to choose as a unitary operators. In the literature, the people call this unitary transformation as a gates. So to define the complexity apart the target states, you need two another objects, the reference state and the gates or the set of the gates. Up to this arbitrariness in defining the complexity of a state is defined as the minimum number of gates that are needed to reach the target states. So this originally originated from the quantum mechanic description of the complexity. But in the time that the Susskind proposed his proposal for the dual of the complexity of states in the geometry, as we know, the theory that is dual to a geometry in an ADS-CFT in general, I mean the dimension greater than 2, is a quantum field theory. So after the paper of the Susskind, the people started to think about the notion of the complexity in a quantum field theory. Let me remind you that two important ways developed after the paper of the Susskind for this goal. The first way is the way that the Myers and his collaborators started in 2017 by using the notion of the Nielsen geometric approach. In this approach, the optimal circuits that I said for you in the previous slide, this optimal circuit can be translated to a minimal geodesics. The minimal geodesic in which geometry? Actually, you can associate a geometry to a space of the unitaries, and then the optimal circuits accordingly translate to finding the minimal geodesics in this geometry. And then the complexity translates to the length of this geodesics. And as I told to you, this procedure is developed by Myers and his collaborators. Another important way that the people initiated in 2017 by to think about the complexity of the states in the quantum field theory, it was by work of the Powell and also Takayanagi. This concept of the complexity is borrowed from the notion or the definition of the complexity according to the path integral. In the path integral representation of the states, you can ask from yourself, is there exist another geometry apart from the flat space that calculating the path integral representation of the states on it would be easier than the flat space? It was a question that the Takayanagi and Powell asked from themselves, and they answered to this question accordingly. They say that the path integral representation of the states is nothing just, it can be related to the partition functions. And then when you ask from yourself which geometry on the calculation of the complexity is easier, can be translated to this problem that the response of the path integral or the partition functions to the change of the metric in the 2 dimensions is encoded in the Y transformations in 2 dimensions, because any geometry in the 2 dimensions is conformally flat. So a flat space and the space that you are searching for it to on it, studying the path integral representation of the state is easier, is actually the Y transformation of the flat space. Okay, so this program is translated to the response of the partition function to the Y transformation. And the response of the partition function in 2 dimensions to the Y transformation is encoded in the Liouville actions. So the saddle point of the Liouville actions is a good candidate for a geometry that on it, studying the path integral representation of the states is easy. And very interestingly, if you do these calculations, you can find, instead of the flat space, the time slice of the ADS space times is that geometry. The geometry that on it, finding the path integral representation of the states is easier than the flat space. And this proposal accordingly is called path integral optimizations. And the complexity of the target states in this language translated to the value of the Liouville action for that solution. I mean, the time slice of ADS solutions. And very interestingly, in 2019, it is shown by Michael Heller and Camargo and other guys that these two seemingly different ways are actually connected together. I mean, the Liouville action of the path-integral representation of the states has a deep connection with the length of the minimal geodesic in Nielsen approach. Okay, let me come back to the geometric proposal. According to the proposal of the Susskind, for a geometry, I mean the geometric object that is dual to the complexity of the states in the dual field theory, they are actually appears in the literatures two different proposals, I mean two independent proposals. It also exists another proposal, but these two proposals that I'm saying in the following are the most important ones. The first one is the complexity volume, and the second one is the complexity actions. In the complexity volume, I mean the geometric object for the complexity of the states in dual field theory. The complexity of the states translate to the volume of external surface meeting the asymptotic boundary at the time slice sigma on which the state is defined. I have shown this external surface in this figure for you with the red color. The states that lives on the boundary of this eternal black hole is defined on the time slice sigma that can be related to the time of right and time of left boundaries. We have a definition for it. And in this definition of the complexity of states, apart that Newton constant, it appears an arbitrary scale that I call as an L of bulk. L of bulk is really an arbitrary scale. And also it depends to the solution. For example, in ADS space-times, it's the radius of ADS, and for black holes, large black holes, it is actually related to the temperature of the, for the solution. So it exists an arbitrariness in the definition of the complexity volume. Another proposal for the complexity of the states in the dual field theory, I mean the another geometric objects, which we call it the complexity actions, is defined as following. The complexity of the states is nothing, just the volume of action in the gravitational region, which action, the action on the Wheeler-David patch. The Wheeler-David patch is defined as the domain of dependency of any bulk pushy surface approaching asymptotically the time slice sigma on the boundary, the same time slice as the previous one for the complexity volume. Interestingly, both of these proposals can describe a region behind the horizon for you. As you can see in the definition of the Wheeler-David patch, I'm in this region, and in the complexity volume, I'm in this region. Both of them are in the behind the horizon, and both of these proposals can describe, can use this opportunity to study that part of the geometry. Since my talk is related to the first law of holographic complexity according to the complexity action proposal, so I should say more about this proposal to you. The complexity action, the action on the Wheeler-David patch, has several terms. The first one is a standard one. It is the action of the Einstein-Hilbert, or action of Einstein-Hilbert plus some higher derivatives, the action of Einstein-Hilbert plus higher derivatives and matters. It is in general gravitational action with the matter. But apart is a standard term for the action of the Wheeler-David patch, we should also consider three different boundary terms. I explain for you case by case. The S of joint is actually related to the intersection of the two null boundary of the Wheeler-DeWitt patch. If you have a Wheeler-DeWitt patch with 4 null boundaries, in the intersection of the null boundaries with the induced metric Q that I wrote in this slide for you, you should add a S of joint. And the original motivation, I mean, the main reason to add into this S of joint is to have a well-defined variational principle for the null boundaries of the Wheeler-DeWitt patch. In the S of joint, the epsilon is a sign factor. We have a dictionary for it. It comes again from the well-defined variational principle of the actions on the Wheeler-DeWitt patch. Omega is related to the orthogonal coordinates up to the null boundaries of the Wheeler-DeWitt patch. Q, as I said, is the metric of the joint of, I mean, the intersection of the null boundaries. And A is logarithm of inner product of L and L prime. L and L prime are actually two null boundaries to each null boundary of the Wheeler-DeWitt patch. They are actually null normal vectors. I will explain a little bit more about these vectors in the next slides. Another two boundaries, one of them, which I wrote for you as S of kappa, is related to the kappa, the non-affinity parameter. This parameter describes that how much the coordinate lambda, which parameterizes the null boundary direction, fails to be an affine parameter. And the last boundary terms that I call the sub-counter terms is added to have a full reparameterization of the null boundaries. The theta is an expansion scalar. L of counter term, similar to the L of bulk in the volume proposal, is an arbitrary scale. Lambda, as I told to you, parameterize the null boundary. Sigma, similar to the epsilon in the S of joint, is a sign factor that, again, we have a dictionary for it. And the expansion scalar related to the metric on the intersection of the null boundaries according to this formula. Okay. Interestingly, Susskind and after that the Myers in 2017 studied very carefully this action for neutral black holes, and then they found that the complexity growth rate for the neutral black holes at the very late times has an upper bound. And this upper bound is twice the average energy of the systems, which in the case of the neutral black holes is actually the mass of the black holes. And interestingly, this upper bound is nothing just the Lloyd bound in the community of the quantum information to define a complexity of the states. And it was the point, I mean, the very important point that after that, the people started to think about the complexity actions more deeply and try to understand, to find its connection to scrambling and quantum chaos, ER equal to EPR and fibers. Before going to the next slide, I should emphasize here that for the charged black holes, up to now, the several proposals appear in the literature for the counterpart of the Lloyd bound when we have a charge. But almost of them have problems. But recently, a paper appeared by Mohsen and his collaborators that they could find a better candidate for the Lloyd bound in the charged black holes that I encourage you to see the talk by Mohsen. Okay, I explained for you about the complexity. Now, let me say something about the variation of complexity, because as I told to you in the next slide, the variation of the complexity will be related to the first law of complexity. But apart that, we have good motivations to study the variation of the complexity. So, the first motivation to study the variation of the complexity is related to the ambiguity that was in the definition of the complexity of a state. One of the ambiguity was the definition or the candidate for the reference states. when you study the variation of the complexity by changing the target states, so the reference states or importance of the value, the reference state will be vanishes. Only anything will be related to the change of the target states and the unitary operators that you have used to find your target states. In the bulk part, also the reference state. If you can forget the reference state in the definition of the complexity, I mean, if you use the variation of the complexity, also will be good. Why? Because as I told to you, the reference state, it was a state that the entanglement entropy, I mean the bipartite entanglement entropy for it was 0. Also, I told to you the proposal of the Swingle that the entanglement is the main building block for the space-time. You can reconstruct the space-time by entanglement. And when the reference state has a a 0 entanglement entropy, so we don't have a good geometrical interpretation for the reference state. So when we study the variation of the complexity, it will be also good for us, because as I told to you, we don't have a good geometrical interpretation for the reference state. Another motivation to study the variation of the complexity is that the variation of the complexity is finite, but the complexity itself has several types of divergences. It is similar to what happened for the entanglement entropy in comparison to the relative entanglement entropy. So the variation of the complexity is a better defined observable than the complexity itself. Another motivation is from the gravitational point of view. From the gravitational point of view, the holographic proposal for complexity define new gauge invariant quantities. So studying their variations under small perturbations may lead to new insight in holography. Last but not least, understanding the first law of complexity may have information about the dynamics of space-time as or more than first law of entanglement entropy. Let me remind you that we have a first law of entanglement entropy by which we can understand at least, or we can find at least the linearized Einstein equations. So the variation of the complexity might be related also to the dynamics of gravitational system, similar to the entanglement entropy. Okay, so by these motivations, I mean, you don't need to the reference states. The variation of complexity is finite, and it might be give you some information about the dynamics in the gravity. The Myers in 2019 with his collaborators think about the variation of the complexity. They study the variation of the complexity in two ways, from the field theory side and from the gravity side. I mean, they study the bulk action, I mean, more precisely, the complexity action in the bulk. From the field theory side, they use the Nielsen geometric approach, and they found that the variation of the complexity, or the variation of the simple circuit complexity, only depends on the end point of the optimal trajectory, and no notion of the object of the unitary transformations remain in the variation of the circuit complexity. It is only depends to the end point of the optimal trajectory. It is very similar to the concept of the first law of thermodynamics. The path that you reach to a new state of a system, it does not matter. Just the final state of the systems is important, and it appears in the first law of thermodynamics. In here, also just the end point of the optimal trajectory appears in the variation of the circuit complexity, so they call it the first law of complexity. In the gravity, they studied the spherical symmetric perturbation of a scalar field on top of the ADS geometry. The action is, I have written for you in the first line, the geometry of ADS in the second one, and they found the change of the complexity actions in the form of the served equations. The general, the final result is at the right side in the last equations. As you can see, just the scalar perturbations appear in the variation of the complexity, and no gravitational contributions appear in the final results. It was the one of the observation of the Myers from the gravitational calculations. But more important than that is that the variation of the complexity actions is a boundary term on the null boundaries of the Villiers-David patch. Okay. It's similar to their observations in the quantum field theory side. They observed that the variation of the complexity is just depend to the end point of the optimal trajectory. In the gravity, they found that the change of the complexity actions, it is a boundary term on the boundary of the Villiers-David patch. These boundary terms just come from the gravitational term, some boundary terms on the null boundary of the Villiers-David patch that I show to you in the red color. But in general, it could be related to the actions, the perturbation of the metric and scalar field, also the inside of the Villiers-David patch. But they found that the variation of the complexity, it just depends to the boundary term on the boundary of the Villiers-David patch. So they call it the first law of holographic complexity. In the first law of complexity, the variation of the complexity was related just to the end point of the optimal trajectory, but in the gravity, it is related to a boundary term on the boundary of the Villiers-David patch. So they call it the first law of holographic complexity. So it is or a starting point. We try to extend these calculations, the gravitational calculations of Myers for the first law of holographic complexity to an arbitrary geometry with some arbitrary perturbations. Let me emphasize again that the work of Myers is related to the ADS backgrounds with scalar perturbations with a spherical symmetry. We extend these calculations to any perturbations and any geometry. To be more precise, the action we have studied is the Einstein-Hilbert-Maxwell scalar theory in d space-time dimensions, in which G mu, A mu, and phi 0 are the metric, gauge field, and scalar field. In the background, delta G, delta A, and delta phi are the perturbation of the metric, gauge field, and scalar field, which are completely arbitrary. Before going to show the final result for the first law of holographic complexity, I should mention two important points and also discuss some definitions for the notations. First, let me say two important points. We assume that the phi 0, the background value of the scalar field is 0, and consider the phi as a source of perturbations. In general, you can work in the case that the metric itself is a source of perturbations, but it is actually some trivial extension of all work. But here in this side, I have assumed that a source of perturbation is a scalar field. So if you consider a scalar field as a source of perturbation, if it is the order of this perturbation is epsilon, then equations of motion require perturbations in the metric and the gauge field to be order of epsilon squared. Moreover, the on-shell action of a scalar field will become order of epsilon squared. So the whole action, and therefore the variation of the complexity action in our calculations will be also order of epsilon squared, but in the following we will omit explicit epsilon factor, but it must be supposed. In the case that the metric is a source of perturbations, it will be changed to the order of epsilon. But the general formula for the first law of holographic complexity that I will show to you in the next slide does not change. Another point that should be considered in our calculations is that the null boundaries of the Wheeler-David patch will no longer remain null under a generic metric perturbations. In order to have psi prime, that is the changing the null boundaries of the Wheeler-David patch by back reaction of the scalar field on the geometry. This null boundary also change. In order to have psi prime as a new null hypersurface where psi itself is null, the change of the boundary should be related to the change of metric. So in our calculations, we consider this very important point that causes some differences between our result and the results of the Mayers. I will show to you in the next slides. To understand our final results that I will show to you, I also need to discuss about some notations. As you know better than me, to describe a codimension to null surface that I call it N in this talk, apart the standard, I mean the standard null normal vector of L alpha, you also need another auxiliary null vector that I call it K. We have chosen a normalization for the inner product of these two null vectors. This inner product we have chosen as equal to -1. We insist that this normalization of the null vectors remain also after the perturbations. And it is very important because, as I will show to you, this constraint, constraint the normalization of the null vectors to be remain as equal to -1 also after the perturbations, introduce a new ambiguity in the first law of holographic complex. I will discuss a little bit more in the next slide. So, by using these two null normal vectors, you can find a projection of any vectors of any space-time vectors to a codimension two null hypersurface, and according to the equation with the green color. Note, by having the L vectors L and K and the projection Q, you can define geometric objects. These all geometric objects are actually appear in the first law of holographic complexity, as I will show to you. The tensors ones are actually extrinsic curvatures of that null hypersurface. Eta and eta bar are actually twists. As you can see, they are the covariant derivatives in the direction, for example, the eta bar is a covariant derivative of the vector K in direction of the vector L projected to the null hypersurface N. Eta and eta bar are actually twists. Omega is a normal connection. A and A bar are tangential acceleration of L and K to N, and kappa and kappa bar, as I told you previously, are non-affinity parameters. Moreover, by having L, K, and Q, you can decompose a general variation of the metric in a space-time to a variation of the metric projected to the null hypersurface and the variations in the orthogonal directions. To have these decompositions, we have introduced a tensor, two vectors, and three scalars that I wrote in the green color in this slide. As I told to you previously in the next slide, the normalization conditions that we have chosen for the inner product of these two null vectors for each null hypersurface impose to you that the variation of the L and variation of K are related to this geometric object, variation of these geometric objects, together with appearance of a new arbitrary functions. These arbitrary functions, again, I emphasize that it comes from these conditions on the normalization of the null vectors. So in this slide, I show to you our final result for the first law of holographic complexity. Let me explain for you again that the blue terms are related for the case that you assume sorry, you have assumed a scalar perturbations as a source of perturbations for the metric and the gauge fields. All the blue terms are for the variation of the actions when the boundary of the Wheeler-DeWitt patch is fixed, but the matter inside of the Wheeler-DeWitt patch, a scalar, gauge field, and also the metric chains, but the boundary of the Wheeler-DeWitt patch is fixed. These are encoded in the blue ones. And the red one, the S with the red color, it means that you also allow the variation of the boundary of the Wheeler-DeWitt patch. Okay, I'm sorry that I written for you the details of the calculations. They are so lengthy, but in the end of the day, the variation of the complexity is as following that I wrote for you in this slide. Let me explain a little bit more these terms to you. I'm sorry. Firstly, the contribution of the scalar field, I mean, this term, this term just appear in the result of the Myers. Let me remind you that the Myers and his collaborators studied the spherical perturbation of the scalar field on the geometry of ABS spacetimes. But we studied a general perturbations on an arbitrary background. So apart the contributions that Myers and his collaborators found in their work, an arbitrary extension to the appearance of the gauge field, we see that the geometrical objects, I mean the gravitational part in the perturbations also contribute to the variation of the complexity actions. All the green ones comes from the gravity. These terms were not appear in the results of the Myers, so they are new. Another distinction between our results and the results of the Myers are encoded in these two arbitrary, this arbitrary function and this arbitrary scale. I mean, variation of beta and L-of counterterm. The variation of beta, I say again that it is related to the normalization of the null vectors. So this ambiguity appears in the first law of holographic complexity. Another arbitrary scale comes from S-of counterterms. And this arbitrary scale, together with arbitrary functions, in general appear the first law of complexity. But we have studied several backgrounds with several perturbations, and we have found that in some cases, L-of counterterm or variation of beta or both of them do not appear in those cases. But in general, these two arbitrary, in this arbitrary function and this arbitrary scale remain in the first law of holographic complexity. And the third distinction between our result and the results of the Myers is that in the result of the Myers and his collaborators, just the boundary on the boundary of the null boundary of the Wheeler-DeWitt patch is appear in the first law of holographic complexity that I indicate for you with the N of I. But all results show that apart the contribution of the boundary terms, the boundary of the Wheeler-DeWitt patch, the null boundary of the Wheeler-DeWitt patch, also the metric in the intersection of the null boundaries also contribute to the first law of holographic complexity. So in general, our result have three extra contributions in comparison with the results of the Myers. The green ones that I told you, they are the gravitational contributions. Second one, the extra ambiguity And the third one, the contribution of the intersection of the null boundaries of the relevant patch. Before to conclude, let me show to you two examples. The first example describes the non-spherical perturbation of a scalar field. I mean this one. I mean you can see that it is the non-spherical information is encoded in this function rho. If you consider these perturbations of the metric that comes from the perturbation that is sourced by a scalar, but it does not has a spherical symmetry, it is actually violate the spherical symmetry. If you use this perturbation of the metric in our general formula for the first law of holographic complexity, in the final day, the result for the variation of the complexity is as follows. As you can see, again, I should emphasize that apart the contribution that the Myers and his collaborators found in their papers, we have two extra contributions. One, first from the gravitational sector of the theory. Also, the gravitational perturbations also contribute to the first law of the holographic complexity that actually originated from the non-spherical perturbations. Also, an arbitrary scale of counter terms appear, and moreover, we have a contribution from the intersection of the null boundaries in our results. Another example, which is more important in our study, and I will discuss more about it in the conclusion, is the case of charging this black hole in four-dimensional spacetime. By using our general formula for the first law of holographic complexity, we can see that the change of the complexity, I mean complexity action or the variation of the complexity action, apart the contribution of matter field as a boundary terms on the boundary of the Miller-David patch, we have extra contributions that come from the gravitational sector. And very interestingly, the coefficients of this contribution is the mass of the black hole or the energy of the systems. So it has a very good, interesting consequences that I will tell you about it to you in the conclusion sections. Let me conclude. To explore, we actually explored the first law of holographic complexity through studying different perturbations around various space-time backgrounds. Other important aspects of our result is that in general, we see that the gravitational perturbations appear in the variation of holographic complexity even in ADS background when we do not restrict ourselves to spherical preserving perturbations. If you restrict yourself to the spherical preserving perturbations, no gravitational perturbations appear in the final result for the first law of holographic complexity. But if you choose the non-spherical ones, also the gravitational sector contribute to the first law of holographic complexity. This is in contrast to the results of the Myers. The other distinction between our work and the work of Myers is that we consider the contribution of the joint terms, and these terms automatically cancel the surface integral when doing integration by parts. In contrast, to remove those surface integrals, the Myers and his collaborators use the non-asymptotic follow for the perturbations. This is another, important distinction between the way we have choose and the way that the Myers is used. We explicitly add the contribution of the joint terms, but they just use the asymptotic follow for the perturbations, and it is another source that we have found a distinction in our results. And the point that was related to appearance of the mass in the complexity of actions, I should tell about it in this slide, is that actually it is our proposals. We propose that the variation of the complexity action or the first law of the holographic complexity can be written as a conserved charge, as a gravitational conserved charge which is a reminiscence of the first law of thermodynamics. In these relations, as I told previously, the sigma is a sign factor. Omega was related to the coordinate orthogonal to the null boundary of the Wheeler-DeWitt patch. Lambda parameterized the null direction in the on the boundary of the Wheeler-DeWitt patch. Delta G in the green color are the projection of the general variation of the metric on the null boundary of the Wheeler-DeWitt patch. And TNBY is the response of the system to the variation, the projection of the variation of the metric on the null boundary of the Wheeler-DeWitt patch. And this TNBY is, you can call it the null Brownian stress tensor, is the counterpart of the Brownian stress tensor, and it is actually related, as I told to you, to the response. It's actually a response of the metric variations projected on the null boundaries. And it has a very interesting consequences. What is the consequences? As I told to you previously, in the Nielsen geometric approach, the variation of the complexity was related just to the end point of the optimal trajectory. Here, the variation of the complexity, it is related just, or it can be written as a boundary term on the boundary of the Wheeler-DeWitt patch. So by pay attention to the definition of the complexity, I mean, and its relation to the construction by path integral representation or in the Nielsen approach, you can conclude that the space-time reconstruction is related to the adding the layers of the null cones together. I mean, in the tensor network of the mirror, you add layers by adding entanglement entropy. You increase the entanglement by layers and layers to reach your final the target states. In the gravity, this can be translated to adding the layers of null cones together to construct the space-time geometry, which according to the ADS-CP conjecture is related to states in the Hilbert space of dual quantum field theory. Also, I can say something about the relation of adding these layers of null cones to reconstruct the RG flows of the Wilsonian renormalization group, and the fixed point of that because I don't have enough time, so I don't say more about it. And for the future work, it would be interesting to calculate the variation of complexity according to the complexity volume proposal and find qualitative and quantitative similarities or differences with the complexity action that we have found in our work. And it would be also interesting to understand better the holographic circuits, gates, and cost functions from our holographic first law. At least a good holographic cost function for neutral and charged solution was found previously, and it is a good area to compare that cost functions to our results for the first law of holographic complexity. So I'm sorry that I violated the boundary of time that you have given to me. So thank you for your attention.
So thank you, Ali, for your talk. Any question, any comments or questions from the audience? So I don't see any.
I have a very, oh, sorry.
Yeah, go ahead.
I have a very general question.
Yeah, go ahead, please.
So in circuit complexity, you always choose a reference state, and typically that is chosen to be a completely unentangled state, kind of a direct product at every point. Is it understood how the various holographic discussions of complexity, what does it imply? What reference state does that imply?
As I told to you, and it is related to your point, I told the Swingle, or the proposal of the Swingle was that the spacetimes can be reconstructed from the entanglement entropy. So when the entanglement entropy itself is zero in the product states, in the reference states, so we don't have a good meaning for the geometry. At least I don't know. And
Yeah.
I understand your questions. But up to now, it does not exist, appear any good candidate for the reference states in the bulk. It exists also proposal by Takayanagi, which might be better than me. It is the surface state correspondence. But in the surface state correspondence, this remains an open problem. Your question, I mean, the geometric dual of the product states. At the moment, I don't know any geometric objects for it.
I guess what I was asking is that, I mean, the two proposals for holographic complexity, it is some definite quantity which you calculate, right?
Yeah, in the holographic side also, the meaning of the reference states is not clear.
I see. That's what I want.
In the holography also the same problem.
Okay.
We have the same problem.
Thank you.
Welcome.
Okay, any more questions? In that case, let's thank